All right, this is November 28th. This is Math 0310, and a couple of announcements here. First of all, Exam 3. The window opens on Thursday, November the 30th, and runs through December the 5th. So please, you need to get the test taken during that window. Remember that we have an Exam 3 review. And let me emphasize, work on the review. This is a good review for this test. And if you can make it through the review and get most of the problems worked on your own without any book or notes or anything like that, then you're going to be in good shape on the exam. Remember that I will allow a scientific calculator on this test. So if you want to, most testing centers in the Lone Star system have scientific calculators that they can lend out. You can also, I think you can bring your own, but it would be better to use the ones that they're going to lend you there. But anyway, you can use a scientific calculator on the test. So if you want a calculator, make sure you bring one with you. That would be the best thing to do. And hopefully that will help you. The arithmetic is not going to be too strenuous on the test, but all right. So I wanted to point that out. On campus hours. I will be on campus tomorrow, so Wednesday. So that's the 29th, and I will be on campus from 4 to 6 p.m. And then on Thursday, 11:30, November the 30th, I'll be on campus from 9 to 11 a.m. So if you can make it to the Lone Star campus, to the North Harris campus, and you have questions, please come on by. I'll be happy to help you out. I have had students come by for the first two exams. Not that many, but I have had some students come by. I almost always do well on the test, the students that are coming in for help face-to-face. So please take advantage of those hours. Online office hours. So Tuesday, I'll be in my office from 1 to 2 p.m. and 8 to 9 p.m. And then I will, since I'm on campus the next couple of days, I won't have any online office hours the next couple of days. The next time we'll be online will be Sunday, and that'll be December the 3rd. Gee, it's hard to believe it's December, but that'll be December the 3rd, and that will be from 7:30 to 9 p.m. And then again on Monday, from that's the 4th, from 8 to 9 p.m. And as we're heading into the final exam, I will be online on Tuesday, the 5th, from 8 to 9 p.m. And on Wednesday, the 6th, I'll be online from 8 to 9 p.m. So take advantage of those online office hours. If you have questions, don't hesitate to stop by. Stop by my online office. Final exam review is posted. This is a departmental review, but it's a good review for the final exam. And so, and it is with your other test reviews for the semester. All the answers are on there also, so you can start working on that. I probably would wait to start working on that until you've taken Exam 3. Remember that the window for the final exam opens on Thursday, December the 7th, and it goes through Monday, and that's the 11th of December. So we got the 7th through the 11th to take this final exam. All right, so that's kind of an overview of some of the things that we've got going on. So I want to kind of call your attention to all those things. Pay attention to WebAssign as always and get those homeworks finished. We're closing in on finishing up WebAssign homework. There's just a couple of assignments left. So today, let's go ahead and flip the screen. Today we're all about, and it's kind of a change from what we've been doing, I guess, in some ways. Today we're talking about absolute value and equations and inequalities. So kind of a lot of different things here. They all kind of fit together. You'll see how it all kind of fits together as we go through this. But this is our topic for the day today. This material will not be on your exam 3. It will be on your final exam. So let me point this out. Not on exam 3, but on your final exam. And so there will be questions on the final that cover this material. So I want to make sure that you are ready for those questions when you get to them. This is important material also as you head into college algebra. And anything beyond college algebra, absolute value is going to be important too. So if you by chance are a science major and you go on and get into the calculus sequence, absolute value is going to be important. Inequalities are going to be important if you're a business major. Then you have to go on and take a business mathematics class for things like linear programming, things like that. So these things are going to crop up for a lot of you in a lot of different places over the next couple of semesters in the coursework that you're taking. So let's go ahead and get this started. And the first thing I need to do is talk about inequalities a little bit. Now, one good thing is that we have talked some about interval notation, so that's going to help when we're talking about inequalities. But now, this is all going to be, we've been talking about things in 2 variables and graphing. We are going back to 1 variable problems, and I should point that out. So when we're graphing, remember, if you're talking about a 1 variable problem, and actually let me go ahead and put that on here before I actually start talking about inequalities. When you're talking about 1 variable equations or inequalities, the graphs are on a number line. Right? That's where you're looking at sketching pictures of things. When you're talking about 2 variable equations and inequalities, then you're talking about the graphs or the pictures of the solution sets are in the coordinate plane. And when I say the coordinate plane, remember I'm talking about, the x-axis, the y-axis, etc. Right, x-axis, y-axis. Right, and because you have 2 variables, you have to have 2 dimensions to what you're graphing. 1 variable problems, you only need 1 dimension. So I wanted to kind of point that out to make sure you kind of have a little bit of a bigger overall picture of what's going on. So we are going back to 1 variable problems. We have been talking about 2 variable problems. We've been talking about graphing. We've been talking about functions. We've been talking about analyzing graphs. We've been talking about inequalities in the plane. Those are all 2 variable problems, and we're graphing in the plane. And so to finish this, we're going back to number lines and talking about graphing on number lines. All right. So if you're talking about just graphing something like x less than or equal to 3 on a number line, not in a plane, but just as a 1 variable problem now. Right? So these are 1 variable problems. So x less than or equal to 3 on a number line, right, is all the x values that are to the left of 3. And we've maybe talked a little bit about that in class, but not very much. And so it's all the values to the left of 3. And so you might shade, and by the way, since it's less than or equal to 3, right, we put a solid dot on the 3, and then we're shading everything to the left in this problem, like so. All right, now in interval notation, and this is something we haven't kind of put together with this, but if you're talking about in interval notation, then the way we write this, and it's good to have the picture of the graph, but in interval notation, this is going to be negative infinity to 3, and then close the bracket around the 3. And remember, a parenthesis always around the infinity. Remember, on a number line, when you're going off to the left on a number line, it's always negative infinity, and when you're going off to the right, it's always positive infinity. So in this problem, we're going off to the left, so we put a negative infinity on the left part of our little interval notation. All right, so that doesn't seem to be too big a deal. X greater than negative 4, then here's 0, and now what negative 4 is not part of the solution set because it says strictly greater than negative 4. So we put an open circle. Remember, that's the standard procedures. Put an open circle on the negative 4. And then since this is greater than negative 4, we're shading everything to the right. Right? And that's the way our picture looks right there. And then in interval notation, for a problem like this, we would start at negative 4. That would be our left edge to the solution set. We'd put a parenthesis around the negative 4 because we're not including negative 4. And then we go off to infinity, to positive infinity to the right like that. Remember, negative infinity is always on the left, positive infinity is always on the right like that. So in this case, since we're going off to the right, we would put the positive infinity on the right part of the interval notation there. All right, so that's fine, and that kind of fits in with things we've been doing. But now we need to move on a little bit from those kinds of inequalities to what we call compound inequalities, and we're going to need this in particular when we're dealing with absolute value. The word compound just means it's a statement that connects two different inequalities. So you might have a statement that looks like this, x less than 1 or x greater than or equal to 4, let's say. Right, this is an example of a compound inequality. It's one statement, but it's got two little statements that are connected, and in this case with the word or. The word or simply means that one of those has to be true, but they don't both have to be true. And so what you're doing here is you're just really just connecting two different sets on the same number line. So you have, if this is 0 right here, then here's 1, and then 2, 3, and 4. And so we'd be shading everything to the left of 1. We put an open circle around the 1, and we shade everything to the left, like so. And then we would put a solid dot on the 4, and we'd shade everything to the right on the 4, like that. And so with a compound statement, it's not uncommon that you see several pieces to the graph like this. And then in interval notation, the only way to write a statement like this in interval notation is to actually use two little pieces of interval notations for each one of those pieces of the graph. And so you'd go from negative infinity to 1, put a parenthesis around the 1 because the 1's not included, and then you go from 4, that one would be on the left, to infinity. You put a bracket around the 4 like that. I'll remember always parentheses around the infinities. And then when you have two pieces like this, you connect them with a union symbol. And that union symbol simply means that we're taking these two smaller sets and we're connecting them together as a bigger set. And so the solution to this compound inequality would be all the numbers less than 1 and all the numbers greater than 4, because all the numbers in either of those sets would make at least one of those two statements true. It doesn't have to make both of them true because of the or statement. Just has to make one of them true. Now, you can also have a compound inequality where you have an and between the two. So we might have something like this. X greater than or equal to -5 and x is less than or equal to 2. Right? So now when you have the word and connecting these two statements, then the only x values that you graph are x values that make both of these true. And so I want you to just make a real rough sketch here. You know, let's say that this is -5 right here, and this is 2. So on one of the sets, you're talking about everything greater than or equal to -5. So you're talking about everything to the right of -5, right? That's x greater than or equal to -5. And then on the other one, the x less than or equal to 2 starts at 2 there, and it's everything less than like that. And that's x less than or equal to 2 right there. Now remember what we're looking for the two, or the numbers that make both of those statements true. And the numbers that make, and the reason why it's both is because of the word and. Well, the only numbers that make both of them true are the numbers that got graphed both times. And the numbers that got graphed both times are all the numbers between -5 and 2. And so this is actually everything between -5 and 2, like this. And that's the set in this case. X greater than or equal to -5 and x is less than or equal to 2. Where it would be everything between those two numbers, -5 and 2. And in interval notation, right, we would put bracket -5 to 2 and then close the brackets like this. There'd be no infinities because you don't have any arrows going off to the left or to the right infinitely far like this. Right? It's just a what we call a closed interval, and this closed interval is everything between -5 and 2. Because it's everything between -5 and 2, a lot of times this kind of statement, we have an abbreviation for this kind of statement. And what we do is we take the first statement, the x greater than or equal to -5, and we actually turn it around. And when I say turn it around, you're literally just taking it and flipping it so that it looks like this: -5 less than or equal to x, and x less than or equal to 2, like that. It's the same statement. All I did is took the x greater than or equal to -5 and just wrote it, instead of left to right, I wrote it right to left. But it's the same statement. And then that actually gets abbreviated like this. Instead of saying -5 less than or equal to x and x less than or equal to 2, you just concisely write this as -5 less than or equal to x, which is less than or equal to 2. And this statement right here is a common abbreviation for this compound inequality right here. In fact, that's the way we will typically write it. But I want you to know that these two actually mean the same thing. And if you get confused at as to what the shorthand version is, you can always write it out as the longhand version. So, for example, if I have -10 less than x, which is less than or equal to +10, let's say, if you had a statement like that, so that's written in that concise form, you could actually break that up as -10 less than x and x less than or equal to 10. And then when you write it that way, that first one, the -10 less than or equal to x, doesn't look good because you really want the x on the left side. And so you flip that one and write it x greater than -10 and x less than or equal to 10, like that. So that's really what that abbreviated version means. And on a graph, the good thing is these always, when you write this concise version, these are always closed intervals, or maybe not. In this case, it's a half closed, half open interval, but it's always just this nice definite interval. You don't include -10 here. You do include +10, and then it's everything in between. like this. And then in interval notation, this would be simply -10 to 10. We don't include -10. We do include +10, like that. So really what I want you to start doing is I want you to start thinking about how these three statements here are all equivalent. Right, the -10 less than or equal to x less than or equal to 10 is the same as that set of all numbers between -10 and 10, including 10. And then that's the way you'd write it out in interval notation, that you need to be able to connect those three ways of writing the statement, okay? And the same with the or statements too. So let me summarize that on the next page. So if you have an or statement, now, or statements are never written in an abbreviated form. So you have x, let's say, less than 0 and x greater than or equal to 5, like that. Oh, I said an and statement, or an or statement, but I wrote the word and, sorry. So that's or right there. So x less than 0 or x greater than or equal to 5. So that would be the or statement. As a number line, right? Let's say that that's 0 and that that's 5 right there. So it would be everything less than 0. We would put an open circle around the 0, and it'd be everything to the left of 0 on the number line. And then x greater than or equal to 5, we'd include 5, a solid dot on the 5, and it's everything to the right of 5 on the number line. So that's the way you draw it out on a number line. And then in interval notation, you'd write these two pieces. So it'd be -infinity to 0 with a parenthesis around the 0, union, bracket there, 5 to infinity. So I want you to understand that those three statements, the inequality, the picture on the number line, and then the interval notation are all the same thing. These all mean exactly the same thing. These are all equivalent. They mean the same thing. All right, and then the and statements. So an and statement is typically written in this nice concise version that we just talked about. So let's say we have -6 less than x, which is less than 12. Okay, -6 less than x less than 12. So that would represent, and we saw on the last page why this would be true. This would be all the numbers between -6 and 12. Right, that's the way an and statement, typically its equivalent version on a number line is everything between two numbers. We put an open circle around the -6, an open circle around the 12, and then we'd shade everything between, like that. And so that would be the number line version of that inequality. And then finally, the interval notation for that would be -6 to 12. We put parentheses around both the -6 and the 12 because neither one of them is included. So these all mean the same thing right here. All right, so those are equivalent. So I want you to be able to go back and forth throughout the various different ways to write out these statements with an and statement or with an or statement like that. Notice that with the or statement, you've got two numbers, and it's everything to the outside of those two numbers. And so, you could think of the word outside as being part of the or statements. You're talking about outside of two numbers. And on the and statements, it's just the opposite, isn't it? It's everything on the inside. So thinking of those two words in association with or statements or and statements is a good thing, I think, to help you kind of keep things straight here. All right, so now the question is, how is all of this, okay, so that's fine, but how is all this connected to absolute value? Oh yeah, one other thing. One other thing I wanted to talk about here before we do anything else. Sometimes, especially, well, with both the or statements and the and statements, it's not quite as simple as what I've written out in that. The inequality might look like this instead. So here's an or statement that's a little bit more complicated. So let's say we have 2x plus 1 is less than or equal to 5. 2x plus 1 is less than or equal to 5, or negative 3x plus 4 is less than or equal to, and let's say we have 8 over here. Let's say 13. Yeah, that'd be better. All right, so now the inequality is not written quite as simple as the first couple. And so the deal is, with this or statement, you simply want to take that or statement and make it look like this one right here. So you want to make it look like that statement at the beginning. And so you simply solve each of these inequalities for x. So you solve for x in both cases. And so to solve for x, with an inequality like this, a linear inequality, do the same thing as you would with an equation. So you subtract 1, you get 2x less than or equal to 4. You divide by 2, and you get x less than or equal to 2. Okay, so no big deal there. Now, the other part, you have negative 3x less than or equal to 9. And I think I probably kind of miswrote this problem. I probably should, that's not something I wanted to do there. So I apologize. This is going to have to be, let's say, yeah, this number right here needs to be something like negative 14, because I want this to work out like a certain way, okay? So when I do that, you'll see what I'm talking about in a second. So when I subtract 4, I get negative 18 over here. So you get negative 3x less than or equal to negative 18. And now you're going to divide by negative 3 on this one. So on this problem, when I divided by 2, no big deal. But remember, in an inequality, when you divide by a negative, you have to reverse the order symbol like that. So that's something that we probably haven't talked about in this class this semester. But when you divide by a negative, and it's actually divide or multiply by a negative, you must reverse the order symbol. So reverse the order symbol. And hopefully that's something most of you remembered anyway, but that's something you probably haven't done in a while. So notice I reversed it right here, right? I went from less than or equal to greater than or equal to. All right, and then remember that this is still an or statement right here. And see now, so now what have we done? We've taken this or statement that looked a little bit complicated, and we made it look like the or statement from the previous page, just like that. All right. And then it's the same as what we've just talked about. You take that statement and you can graph that on a number line. So let's say that that's 2 and that's 6 right there. This would be including 2 and including 6. And it's everything to the left of 2 and everything to the right of 6, like that. And then in interval notation, this would be written negative infinity to 2, bracket, and then a union symbol, and then bracket 6 to infinity, like that. All right, so the only thing that we're adding on are these steps here at the beginning is that you need to solve for x at the beginning on a statement like this. And then it works out pretty much the same way as we've been talking about. Now, an and statement might look a little bit different here, but you're doing exactly the same kinds of things on this problem, or on an and statement. So it might start out by looking like this. Let's say we have negative 8 less than or equal to 3x plus 4 which is less than, let's say we have 13 right here. Now I'm going to use 13, and it's going to be fine. All right, so when you solve for x on this one, on a compound statement like this, when you solve for x, what you're trying to do is just get the x by itself, because now you want it to look like this and statement. So you want to get the x by itself, just like this one, the second one on this page was. So, you want this x less than or equal to and a less than like this. And so you just have to remember that when you subtract 4 to solve for x, that you have to subtract 4 on all 3 parts of the inequality like that. So when you do that, you get negative 12 less than or equal to 3x, which is less than 9. And now what's the next step is going to be divide by 3. I'm dividing by a positive, so this is no big deal as far as the inequalities go. Don't have to reverse anything. I divide everything by 3. And I get a statement when I'm done here that looks like the problem on the previous screen. All right, so you get negative 4 less than or equal to x, which is less than 3. All right. And then on a number line, this would represent all the numbers between negative 4 and 3, including negative 4. So we put a filled-in dot at the negative 4 and an open circle at the 3, and we'd shade everything in between, like that. And then in interval notation, we'd write negative 4 to 3. We put a bracket around the negative 4 and a parenthesis around the 3. All right, so all we're doing here is we just added on these first few steps here at the beginning, and then we make the problem look like the last screen, and then we can graph it and write it in interval notation. All right. So now let's go on to absolute value, and let's talk about how this all relates to absolute value. So if we talk about statements like this, so we're going to talk about 3 different kinds of statements with absolute value. And let me remind you again that the absolute value of a positive number is just itself, and the absolute value of a negative number is the opposite of itself. That absolute values are always equal to positive numbers, right? Except for absolute value of 0, which is just 0. All right, so what we want to do is we want to look at equations. And so when I talk about an equation, I'm talking about something like this. The absolute value of x is equal to 5. And then we want to look at inequalities. So an inequality would be the absolute value of x maybe is less than or equal to 5. Or you could write the absolute value of x is greater than or equal to 5. Right? You have less than statements and greater than statements there. So those are the kinds of statements we want to look at here and think about what the solutions to these might look like. All right, and so we're going to take these 3 statements, in fact, and we're just going to put them right next to each other and compare how these work out. So you have the absolute value of x equals to 5, and then we're going to kind of put a vertical dashed line there, and then we're going to put the absolute value of x less than or equal to 5 right next to it, and then separate that, and then absolute value of x is greater than or equal to 5, like that. So you can kind of compare these two and see how they all work. Now the absolute value of x equals 5. Think about at the very top of the page, I said, like the absolute value of 8 is 8, the absolute value of negative 3 is 3. So you're saying to yourself, what numbers have an absolute value equal to 5? And there's actually 2 numbers that have an absolute value equal to 5, because if you think about what we talked about at the top here, that x equals negative 5 would make that true, or x positive 5 would make that true. And so you get x equals negative 5 or x equals positive 5. Those are the 2 numbers that have an absolute value equal to 5. On a number line, all you'd be doing, there's no inequality here, so there's no shading to do. All you're doing is plotting negative 5 and putting a closed dot there and positive 5 and putting a closed dot there. And that's the graph of your solution set, right? Are just those two numbers. You would not use interval notation here at all, right? All you'd do is put -5 and 5 in braces, and you'd be finished with the problem, right? Just list them out. There's just those two solutions. Now, the next problem, the less than statement, if you think about this one for a second, and we're going to do this one kind of backwards. We're going to do this one on the graph first, and then we'll write out the inequality and the interval notation for this. On the graph, if you think about it, you're looking for the numbers whose absolute values are less than or equal to 5. And if you think about that for a second, numbers, if you take a number and you've got to have its absolute value being less than 5, well, that could be a number like, so let's say that this is 0 right here. A number like -2, let's say that's sitting right there, its absolute value is +2, which is less than 5. So -2 is a solution to this inequality. You could look at 3, and the absolute value of 3 is less than or equal to 5. So this is a solution to this inequality. But if you look at 6, the absolute value of 6 is not less than 5, so that's not a solution, right? Same thing with -6. It would not be a solution either. The only numbers that make this a solution that make this true are all the numbers that are between -5 and +5. So let's say that that's -5 right there, and that's +5. These are the numbers that make this statement true. Now, what does that graph look like? Does that graph look like the AND statement or the OR statement? Does it look like an inside problem or an outside problem? Well, this is an inside problem. This is an AND statement problem. And so that's how we write an inequality, an absolute value inequality like this, as an inequality without an absolute value, is we just write this as a typical old AND statement. This would be -5 less than or equal to x, which is less than or equal to 5, like so. And then in interval notation, we would use interval notation here, and this would be bracket -5 to 5, and then close the brackets like that. All right, so what do we see with less thans? That these are AND statements. And this number that's inside the absolute value, where is it? This number right here is x. Where is it? It's between -5 and 5. And then you're looking in the last one with numbers whose absolute values are bigger than 5, bigger than or equal to 5. And if you think about that for a second, you would come up with the idea that the number has to be the number itself has to be bigger than 5, regardless of the sign. So the absolute value of 8 is 8, which would be bigger than 5. Absolute value of -10 is 10, which is bigger than or equal to 5. So 8 and -10 are both solutions to this inequality. And so here's -5 and 5. You are, in this case, talking about everything bigger than or equal to 5. So everything over here to the right of 5, and everything less than or equal to -5, it's everything to the left of -5. And, a graph like that, which one of these statements does it look like? Well, now it looks like the first one. Now it's an OR statement problem. This is an outside problem, right? So everything outside of these two numbers. And so as a compound inequality, we would write this as x less than or equal to -5 or x greater than or equal to 5, like so. And then in interval notation, this would be -∞ to -5, close the brackets, and then union 5 to infinity, like that. And this is an OR statement in this case. Right? It's an outside problem. This one's an inside problem. The less than is an inside problem. The greater than is an outside problem. All right, so this kind of helps us kind of keep this straight a little bit. So now what I'm going to do is kind of write down some general statements here so that we can take somewhat more complicated absolute value statements and write them out like we've been doing. Okay, so if you have an equation, so let's say we have the absolute value of Bob. So when I write Bob there, I'm saying that this is possibly a more complicated thing than just an X. Right, so there's Bob. And, because on these first problems, what did I do? I just put an X inside the absolute values on these first three. So let's say it's something more complicated. That's why I mean what I mean by Bob right there. Make sure that O looks good. And let's say it's equal to K, but absolute value of Bob is equal to K. Then on a number line, the solution would simply be that Bob is equal to either negative K or Bob is equal to K, right? So that's Bob in each case. So Bob is either equal to K or Bob is equal to negative K. And so we'd write that out. Bob is equal to negative K or Bob is equal to positive K in this case. Now, by the way, one thing I haven't written down here is, we're assuming, remember, absolute values are always equal to positive numbers. And so we're assuming here on all these statements that K is positive, that all this is true if this number K is a positive number. And we do need to talk about what happens if K is negative. And we will talk about this. But right now, let's assume throughout this entire screen that K is positive, or it could be 0. Right? We want K to be either positive or 0. So what do you get here? That Bob is either equal to negative K or Bob is equal to positive K. And then we could finish out the statement from there. All right, so now that's the equation. So now the inequalities. So let's say we have the absolute value of Bob is less than or equal to K. Now, so remember the less than from the previous page was an inside problem, right? And so what we have here on a number line is we would have negative K and K. Here's negative K and here's K right here. And where is Bob in this case? It would be inside, and so Bob is between negative K and K. So as a compound inequality, this would be negative K less than or equal to Bob, which is less than or equal to K. Now remember, Bob might be a little bit more complicated of an expression, and so we may have to do some work after that, but this would set up the problem for us. Remember that this is an inside problem, and so you get that kind of inequality, or that kind of picture on the number line, I should say. And so Bob is everything in between like this, and then we would finish out the statement from there. Okay, and then if we have the absolute value of Bob greater than or equal to K, this would be an outside problem. So on a number line, we would mark K and negative K, like that. And where would Bob be located in this case? Well, Bob would be either to the left of negative K, like that. So Bob would either be here, or Bob would be over here. Right, Bob is on the outside in this case. And so what do we have as an inequality? We have that Bob is less than or equal to negative K, or Bob is greater than or equal to positive K, like that. And so what we're doing here is we are looking at kind of classifying the statement at the beginning that we've got, and then from that, we can kind of what we're trying to do is write the statement out without absolute values so we can actually come up with some kind of a solution at the end of the problem, right? We're trying to solve these and draw pictures of the solution sets to these statements. And the only way to do that, ultimately, is to get rid of the absolute values. And so what we're going to do, exactly like I've got this labeled right here, is we're going to first draw out the picture. And then from the number line, kind of the general picture from the on the number line. And then we're going to use that picture to write out either an equation or an inequality, an and inequality, or an or inequality. And then from that, actually solve the problem and actually solve the inequality or the equation, right? And come up with a solution at the end. All right, so now I would think that you'd probably be a little bit uneasy as we go through this at the beginning because you're still not exactly sure how this is working. So when you start seeing some problems, hopefully it'll start making a little bit more sense. So I'm going to put two examples kind of right next to each other here at the bottom. So let's say we have the absolute value of x plus 3 is equal to 4. So notice that the expression inside the absolute values is not like these here at the bottom of the screen. It's not just an x inside the absolute values. It's a somewhat more complicated expression. In this case, it's x plus 3. That's our Bob in this case, right? And so this is like the first picture right here. And what do we know? That Bob at the x plus 3 is either got to be equal to negative 4 or 4, right? We put negative 4 right here, and we put 4 right here. And we know that x plus 3, that's our Bob in this case, has got to be equal to one of those two values, right? That x plus 3 is either equal to negative 4 or x plus 3 is equal to positive 4. There's nothing to shade for an equation, remember. And so what do we have here? We have that x plus 3 is equal to negative 4 or x plus 3 is equal to positive 4, right? Just write out the equation from that picture. And then solve each of those two equations, and you get x equals negative 7 or x equals 1. And there you go. There's your solutions to this equation, right? And we get negative 7 and 1 are the solutions. Don't forget, you can check this, and I would strongly recommend you check to see that you've got this right. You know, if you take negative 7 and substitute it in place, let's check x equals negative 7 here. So you have the absolute value of negative 7 plus 3 equal to 4. So that's the absolute value of negative 4 equals to 4, and sure enough, that's true, right? And then 1 does the same thing. If you check x equals 1, you get the absolute value of 1 plus 3 equals 4. So that's the absolute value of 4 equals 4, or 4 equals 4. Right? And so the two solutions to this inequality are negative 7 and 1. All right, so there's an example right there. And I left enough room that I think I've got enough room for another example here. It'd be nice to have these kind of sitting next to each other, to be honest with you. So let's say we have the absolute value of x minus 2. So now Bob is a little bit different of an expression. It's x minus 2. And it's less than or equal to 3. The absolute value of x minus 2 is less than or equal to 3. So this is like the middle picture right here. This is an inside problem. And when I draw out the number line here, I would put automatically negative 3 and 3 on the number line. And where does Bob have to be sitting in this problem? Well, Bob has to be sitting inside those two. So Bob is sitting right here. Well, and I'm not going to write Bob there because Bob we know is x minus 2 in this problem. So x minus 2 has got to be between negative 3 and 3. So then you just write this out as an inequality. Negative 3 less than or equal to x minus 2. There's my Bob sitting between, and that's less than or equal to 3, like that. Right, so you get that kind of a compound inequality. And then just solve that, add 2, and you get negative 1 less than or equal to x, which is less than or equal to 5. And then as a interval notation, this would be bracket negative 1 to 5, close the brackets. To check this now, what I would do here, and let's go ahead and write out this inequality again on the next page. So this was our inequality, absolute value of x minus 2 less than or equal to 3. And our solution that we got was the bracket negative 1 to 5, right? That was the solution, negative 1 to 5, like that. So what we're saying ultimately here is that the solution is everything between -1 and 5. Right? We're saying that the solution to the inequality is all these numbers right here. And so what you might want to do to check this is you might want to pick a couple of numbers on the number line and see if they fit what our solution looks like it's going to be on the number line. So like you could pick a number over here like -2. So we might check. Now look at, is -2 shaded? It's not. And so what should happen here when I check -2 is I should get a false statement. So I check x equals -2, and I'm going to write should be false because it was not shaded. So what do I get? Absolute value of -2 minus 2 less than or equal to 3. Absolute value of -4 is less than or equal to 3. And you get 4 less than or equal to 3. False. Right? Like we thought it was going to be. All right, so now pick one that's shaded like this, in the middle somewhere, between -1 and 5. Any number in between would be fine. So let's say I pick 3. So I check x equals 3, and this should be true. And so I've got absolute value of 3 minus 2 less than or equal to 3. So that's the absolute value of 1 less than or equal to 3. And you get 1 less than or equal to 3. That is a true statement. And then finally, you could pick something like 6 or 7 or whatever. Something bigger than 5. So I check x equals 6. And from my number line, this should be false because 6 was not shaded. So when you do that, you have the absolute value of 6 minus 2 less than or equal to 3. So that's the absolute value of 4 less than or equal to 3. And you get 4 less than or equal to 3, which is certainly false. Right? And now I'm not saying you have to go through all of this every time on a problem like this, but this would not be hard to do mentally. Just go through the arithmetic in your head, kind of check through the number line that you're drawing out at the very end of the problem and seeing if that actually makes sense. Okay? All right, so what have I done now? I've done an equation at the very bottom. The absolute value of x plus 3 is equal to 4. I've done a less than, absolute value of x minus 2 less than or equal to 3. So let's do a greater than now. So I have the absolute value of x minus 6 greater than or equal to 1, let's say. All right. So let's flip the screen back for a second. And we're looking at the greater thans in this case. So the greater than is an outside problem, right? Where Bob is outside of -k and k. All right, so in our problem here, the k value is 1. So on my number line, what would I do here? I put -1 and 1. So I put -1 and 1 on my number line here. Like that. And I need this to be, remember this is an outside problem. Right, so where's x minus 6 going to go? X minus 6 is either going to be over here, less than or equal to -1, or x minus 6 is going to be over here and greater than or equal to 1. All this does, this is not the solution to the system. All this is going to allow you to do is write out the inequality. That's the only thing this initial picture is for. But I think it's helpful to do this. And so what do we have here? We have x minus 6, looking at the picture, has got to be to the left of -1, so that's less than or equal to -1, or x minus 6 is to the right of +1, so x minus 6 is greater than or equal to 1. Right, and now we have it written out as an inequality. And then just solve each of those, and you get x less than or equal to 5, or x is greater than or equal to 7. And so there's your inequality. And then from there, you can draw out the actual picture of the solution set. Right here's 5 and here's 7. They're pretty close together there. And so when you shade, it'll be everything to the left of 5 and everything to the right of 7, like this. For my solution, and in interval notation, this would be negative infinity to 5, bracket there around the 5, union, and then bracket around the 7, and then to infinity like that. All right, and so we've got the statement at the end. And remember, we're after the number line and we're after the interval notation at the end. And again, you could check this to see if this worked. So notice that if you pick a number between 5 and 7, like you could pick 6, you know, if you just put 6 in there, you see that in for x, right, you get absolute value of 0 greater than or equal to 1 or 0 greater than or equal to 1, which is false. And notice that should be true. And that's right there, right? It should be false because where was 6? 6 was sitting in between here. 6 was not shaded on my final number line there, and so it should not be a solution to this system or to this this inequality. All right. So let's say let's look at something maybe slightly more complicated. Let's say we have the absolute value of 3x minus 5, and this, let's say this is less than 10. 3x minus 5 is, the absolute value of 3x minus 5 is less than 10. So this one is a less than statement. And so this is a between problem or an inside problem, right? This is an inside problem. And on my number line, what am I going to do? I'm going to put negative 10 and 10 on the number line, negative 10 and 10. And our bob in this case, which is 3x minus 5, has got to be between those two, right? 3x minus 5 has got to sit inside here like that. So on a number line, or as an inequality, this would be negative 10 less than, just less than, 3x minus 5, which is less than 10, like that. We'd write it out as an inequality. And again, the only reason I drew that first number line there was just so I could have a good visual of how this was going to get written out as a inequality. Now you solve this inequality like we've talked about earlier in the lecture today. So I could add 5 to all three parts here, and I get negative 5 less than 3x, which is less than 15. And then I divide by 3. 3 is positive, so I don't have to worry about the order symbol changing. And I get negative 5/3 less than x, which is less than 5. And there's my inequality for this particular absolute value inequality here. And then on a number line, what would I do? I'd put negative 5/3 here and 5 here. These are both less thans, and so these are going to be open circles around negative 5/3 and 5, and it's going to be everything in between like that. And then in interval notation, I would use parentheses because these are both open circles. And so it's everything between negative 5/3 and 5, parentheses around both the negative 5/3 and the 5. Ultimately, you know, these are both what I'm after right here. Is I'm after the number line and I'm after the interval notation. And really, I'm actually after all three at the end. I should say that. Maybe I should, you know, what have you got here? You've got the interval notation, you've got the number line, and you've got the inequality, right? Those three things are all equivalent. And I'd be looking for all three of those statements for an absolute value inequality like this, right? All right, so we're doing good. We're doing good. Let's look at another problem. It has a little bit of a complication, and then let's look at what happens when that number out there is negative and what happens there. So let's say we have the absolute value of 6 minus 3x. Is greater than or equal to 8. All right, the absolute value 6 minus 3x is greater than or equal to 8. So because it's a greater than statement, and based on what we've done so far in lecture today, this is an outside problem, right? And so you've got negative 8 and 8. And Bob, in this case, our 6 minus 3x, is got to be outside of those two numbers. So 6 minus 3x has got to go over here, or 6 minus 3x has got to go over here. Right? That Bob expression always goes on the outside of negative 8 and 8 in this case. So then you write those statements out as inequalities. So you have 6 minus 3x is to the left of negative 8. So that means 6 minus 3x is less than or equal to negative 8. And then or 6 minus 3x is greater than or equal to positive 8. Okay? And so you've got the inequalities written out. Now I solve the inequalities. So in the first problem, I subtract 6. And so you get negative 3x less than or equal to negative 14. Be careful, because now you are dividing by a negative. So this is x greater than or equal to 14 thirds. Remember, you have to reverse this order symbol when you're dividing by a negative. On the next problem, again, you subtract 6. So you have negative 3x is greater than or equal to 2. Right? We're subtracting 6 on both sides. And then, again, you're dividing by a negative. So this order symbol changes direction. And you get x less than or equal to negative 2 thirds. All right, and so that's those are our inequalities. Now the negative 2 thirds is less than 14 thirds, so it's usually written, by the way, it's not wrong to write it this way, but it's usually written with the piece that's going to be on the left, write that first. So x less than or equal to negative 2 thirds, or x greater than or equal to 14 thirds. It doesn't matter, but it's usually written that way. So in a number line, here's negative 2 thirds, and here's 14 thirds. These are both great. These both have equals on them, so these are both solid dots, and we shade everything to the left of negative 2 thirds and everything to the right of positive 14 thirds. And then in interval notation, this would be negative infinity to negative 2 thirds. Close that off with a bracket, and then bracket 14 thirds to infinity. So here are the three things I'm looking for, right? The inequality statement, the number line, and then the interval notation right there at the end. All right, does anybody have any questions? So hopefully we're okay here. Nobody is shouting at me, so I'm assuming that that means we're good with these statements. So when you start off, what do you have to do? You have to classify the problem as either an equation, which means you just got the two dots, or is it an inside problem or an outside problem, right? And then just draw it out from there. All right, now what if the constant is negative? What if k is negative? So when I say that, I'm talking about something like this. The absolute value of x plus 2 is equal to negative 6. See, and remember, what is the absolute value of a number? So remember, the absolute value of anything is always equal to a positive number. It's always equal to a positive number. And so x plus 2 equals negative 6. How can an absolute value be equal to a negative number? Right, that's the question. How can an absolute value equal a negative number? And the answer is, so that's our question, and the answer is it can't. It's not possible. right? The absolute values are always equal to positive numbers or 0. And so the absolute value of x plus 2 equals -6 is never true. It can't be true. No way. And so what do you write here as a solution set? You just simply write no solution. So when you have the absolute value in general, then, if you have the absolute value of Bob equals a negative number, no solution. Right? No way that that could ever be true. All right, so that's the equation. So let's look at the inequalities. So let's say we have the absolute value of 2x minus 1 is less than or equal to -8. So remember, the absolute value of 2x minus 1 must be equal to a positive number, right? So, so the absolute value of 2x minus 1 is positive, or 0. The absolute value, so this number right here is positive. So when is a positive number? That's a question here. When can a positive number be less than a negative number? And so that's the question, and the answer here is never. Right? A positive number is never less than or equal to a negative number. And so what's the moral to the story here? If you have the absolute value of Bob less than or equal to a negative number, right? If that's a negative number sitting over there, then once again, this is no solution. There's no way this can be true. Right, so if you have the absolute value of something less than a negative, no solution would automatically be written down. All right, so that leaves the greater thans, right? So the absolute value of 3x minus 5 is greater than or equal to -3. So remember, the absolute value of 3x minus 5 is positive. The absolute value of 3x minus 5 represents a positive number. Or 0. So this is a positive number right here. And so the question is, when is a positive number? So that's our question here. When is a positive greater than a negative? And the answer in this case, be careful now, the answer in this case is always. Right? A positive number is always greater than a negative number. And so the moral to the story here is the absolute value of 3x minus 5, or for just in general here, the absolute value of Bob is greater than or equal to a negative number. Everything is a solution. And so that means all reals are solutions. It's always true. In interval notation, this would be negative infinity to infinity. All right, so to kind of summarize here, the whole deal, then you have the absolute value of x minus 2 equals 10. And what do you do here? You put -10 and 10 on the number line, and x minus 2 has got to be equal to one of those two values. right? X minus 2 is equal to negative 10, or X minus 2 is equal to positive 10. And then you finish the problem. If the absolute value of X minus 2 is less than or equal to 10, right? Then you have negative 10 and 10 on the number line. This is an inside problem. And so Bob has got to be between these two, right? Here's X minus 2 is inside. And so you get negative 10 less than or equal to X minus 2, which is less than or equal to 10. If the absolute value of X minus 2 is greater than or equal to 10, what do you have here? This is an outside problem because it's a greater than. And so you put negative 10 and 10 here, and X minus 2, or Bob, would have to be out here, or Bob would have to be out here. So X minus 2 is either less than or equal to negative 10, or X minus 2 is greater than or equal to positive 10. And then, if the number is negative, if you have the absolute value of X minus 2 is equal to negative 10, now the number is negative, this is no solution. Right? A positive can never equal a negative. The absolute value of X minus 2 is less than or equal to negative 10. A positive can never be less than a negative, so no solution here. And then finally, if the absolute value of X minus 2 is greater than or equal to negative 10, everything is a solution. So here you have all reals, because a positive is always bigger than a negative. All reals, where you write negative infinity to infinity for the solution set. So this kind of summarizes the whole picture here we've been talking about with absolute values. So hopefully this kind of brings everything back together here at the end. So, all right, so that actually does it. We have finished what we're going to discuss in intermediate algebra. There's no need for a lecture next Wednesday. You remember, I don't lecture this Thursday because that's during our test window. I don't lecture next Tuesday because that's during our test window. And next Thursday, there's no reason to have a final lecture here at all. And that's the beginning of our final exam window there at the very end. So now it's just left for you to work on your web assigned homework, prepare for exam 3, prepare for the final exam. Remember, I am going to be available lots of times, both online and on campus over the next week. So please don't hesitate to try to get in touch with me through WebEx or by email or WebAssign. I'll be happy to try to help you out with anything that you've got. Remember that there's a review online for exam 3. There's also a final exam review that's online on my Google site for the final exam. So you've got lots of things that you can be looking at to try to finish up the course. Does anybody have any questions that they want to ask about?
I'm good.
All right, so then it sounds like everybody is okay. Either I've got a chat message by everybody or verbally I've heard from you. So you guys have a great day. Please don't hesitate to come by my office tomorrow or Thursday if you want to ask some questions. I'll be happy to help you out. Otherwise, have a great week and good luck, not just in my class, but all the rest of your classes with final exams as you finish up the semester. Have a great day.